Hey there, I'm Joe Weems. Before we get into the video, I want to remind you about ng-conf-2023 happening in Salt Lake City, Utah on June 14th and 15th. Head over to ng-conf.org to check out the speakers, check out the talks, and to get your ticket before they all sell out. We'll see you there.
Hello? Anyone there? Where am I? Oh, there is other people here. What's going on? My head's killing me. Do you know how I got here? What's with the massive screens? Last thing I remember, I was at home in New Zealand. Sorry, I should introduce myself. My name's Craig, I'm an Angular GDE, and I'm currently working at Good Code, focused on user experience for cybersecurity products. What the hell? What? What is this? Who is that? I've sent you a teacher. Is that me? This is messed up. I have no idea what's going on, but I guess we have no choice but to just play along. The walls, they're covered in writing. Can someone just shine a light up there, please? Is that TypeScript? What the hell? What's going on? Looks like the website updated. There's just a text input. The bottom of it, what does that mean? Let's check out the code on the walls for some clues. Okay, so TypeScript. Do you all know TypeScript? I'm still a bit groggy, but I can walk us through some stuff and see if we can figure out what's going on. Definitely seen this before. It's the TypeScript type system expressed as a Venn diagram. The big circle represents all valid values. Within all the values, there are some that can only be assigned to specific types, like strings or dates or booleans or custom types that we define. Each type gets its own smaller inner circle with its own set of valid values. The TypeScript type checker has the job of checking the values in our code and the types match up. If we declare a string variable and assign a string to it, the compiler will be happy. Same with booleans and booleans. If we try to assign a number to a string, the compiler complains. But if we give a variable in any type, we can now assign any value to it. Because the any value can be assigned to any variable, we can put any right in the middle of the Venn diagram. In type system speak, a type that can have any value assigned to it is called a top type. TypeScript actually has two top types. Along with any, there's another called unknown. Any value can still be assigned to an unknown variable, but it's a little bit more restricted than any. Since unknown is also a top type, any value can be assigned to unknown, and it lives in the middle of the Venn diagram along with any. So unknown is also a top type. Okay, so top types are types that can have any valid value, and they live inside the circle. But outside the circle, we have the type that has no valid values. In TypeScript, that's called never. No matter what the value is, it can never be assigned to a variable with the never type. The compiler will never allow it. So never is the complete opposite of the top types, any and unknown. And that's why it's the bottom type of the TypeScript type system. Oh, wait a sec. The clue. The bottom. Oh, can I type? No. Huh. That's it. We got it. What happens now? Do you think we can get out of here? Oh, God.
Do you see how the tone is protected? It wasn't always like this. Not long ago, everything was a string, and a simple tablet could work an entire application. We settled. Well, we will see if you can string together a solution. Time to go and read.
What the hell? There's more. I really don't like this. But looks like the website updated. That's a template literal type. Okay, so whoever they are, they're really salty about strings. What did it say? String together a solution? I guess we better keep going along with this. And I guess this is meant to be some kind of clue. Narrow the playing field. I guess we need to talk about type narrowing. Type narrowing means taking some broad set of types with a set of possible values and reducing the set to a smaller number of allowed values. The top types, any and unknown, are the most broad, since they have all possible values, and the bottom type, never, is the most narrow, since it has no possible values. If we have this function, shout, it takes a string and returns a string with an exclamation added to it, we can try to pass a variable with an unknown type to the shout function. But it doesn't work because you can't assign unknown variable to the broad type because it's more broad. Input could be a string, but the type checker can't know that for sure. So we need a way to narrow the type from unknown to string. One way to do that is with the typeof check, which is a runtime check, but also a compile time guard. The type checker can statically analyze this code and be sure that within the block of the if statement, the input must be a string. But string is actually quite a broad type as well. All possible combinations of characters can be assigned to string. Let's say we have some specific set of strings that we care about, defined as a string union type. How do we narrow down to those types? Here we have a string union type of some specific strings that we care about. And we can use a type guard to convince the type checker that some unknown typed variable is actually a help type. A type guard is a function that returns a Boolean, but uses the special is syntax to tell the type checker that if true is returned, then the input must be the specified type. The is help type guard returns true when the input string is in this helps array. Again, the type checker can statically analyze this code and understand that if the if condition passes, then within the if block, input must be one of our expected strings. And again, the set of all strings is larger than the set of strings that end with an exclamation, if we wanted to talk about the return type of our function. It'd be impossible to write out a union of all those possible strings that end with an exclamation, but there's another way we can express that, with a template literal type. This template literal will only match strings that end with an exclamation. While it looks just like a template string, instead of operating on string values, they operate on string types. And there's a whole bunch of ways that we can manipulate these literals. We can use uppercase and lowercase to transform the characters within a type, and we can even combine them to make other types. In this case, the resulting type will be a literal string union, of all possible matching string combinations, which can get quite big. It seems that to solve this next puzzle, we need to find a string that matches the shown template type literal. So in this case, we can just enter the characters that are available. So that, then Oh, that, and that, and that, and that. For the string part, we can type anything, because anything's going to match that. And then we match the rest of the characters, and hopefully. Awesome, we got that one too.
Is in TypeScript console. Perhaps you are generic, unappreciative web engineers after all. Maybe there is still a chance you will get out of here. If only you had a map.
I'm getting kind of annoyed by this. Who does this person think they are? We're grateful. We love TypeScript. Oh, the site updated again. Another puzzle. And more TypeScript, of course. This is getting pretty hardcore, but I want to prove them wrong. So, template literal types showed us some ways to combine different types. Let's look at uppercase again. Uppercase is a special intrinsic string manipulation type. It's a type that manipulates a string type. We can kind of think of it like a function that operates on string types. The syntax might look familiar if you've used arrays or promises, which are generic types that take parameters. We pass a type to array to make a more specific kind of array. And generics are just one of many ways to combine types together. We can explicitly define string unions, or as we've seen, define template literal types. We can even just give types names for things that make it more readable. Creating and manipulating types like this is really necessary to express complex JavaScript concepts. What if we have a plain JavaScript object like this? How would we express the type of this object? Given that we don't necessarily know all the keys, we might say that it's a record with string keys and string values. But we can also express it in another way. Instead of using a record, we can implement this as an object with an index signature. This index signature says that all properties of the object will have a string value, even if they haven't been explicitly named beforehand. This means that we can look up a random property on the type using an indexed access type and confirm that it is, in fact, a type string. We can take this manipulation even further with mapped types. Here we can define a new type called make_grateful, which takes a type parameter, like a generic type does, and creates a new type where all keys of the output type will have the type grateful. We can pass our original victim status type to the make_grateful mapped type and confirm that all the new type properties have grateful as their type. But map types not only allow us to map from the type of a property, but also the name of a property. If we start with an object with named properties, we can define another map type and use the as syntax to manipulate this property name. Here, we're using another template literal to define a type with a prefixed heart emoji. To leave the type of the property unchanged, we can use indexed access type to look up the type of the original property on the original object. If we start from a regular JavaScript object mapping with names to strings, we can ask the compiler for the type of that using typeof, and then pass that to our make memorial mapped type. By adding as const, we tell TypeScript that we just want these specific string values rather than a generic string-to-string mapping. We can then look at the mapped property name with the heart emoji and get back the string type of the property. If we try and use the old property name, we'll get a type checking error because the old key doesn't exist on the new type. More generally, map types look something like this, where A is some input type, B is the union type of all the keys of A, C is some mapping for the set of keys, and D is some mapping for the type of each key. It looks like we need to match up the bits of the code with their corresponding letters in the list. So A is the input that we're mapping over, so it probably actually is victims. But B is the union type, so this is probably going to be under B. And then it looks like we are trying to map to functions. So we are swapping these two around so that the new key is going to be the old victim's name, and the new value, the new type, is going to be a function that returns that name. Cool. We got it again. And I gotta be honest, I kind of get what the video psycho was saying. TypeScript's amazing, but do they have to be such a weird gatekeeper about it?
It looks like you're starting to appreciate how powerful your tools are. Maybe you will make it out of here after all. There are a few final occasions. Let's see if you can extend yourselves.
All right, I'm sick of being condescended to. Let's see if we can figure out who this person is. It's hacking time. Let me just try a few things here. It looks like there's some encoded messages being sent back and forth to start the game. I wonder if we can break it.
What do you think you're doing? Stop that.
Looks like someone isn't happy. We must be onto something. There's definitely a pattern here and some kind of sequence within these strings, but there's also a lot of noise. We need to find the valid strings and extract the useful information. Our genius kidnapper has left us everything we need to figure out their identity. Conditional types let us make decisions based on the state of our types. Conditional types are always written in the form A extends B, then C else D, where A is some input type, B is some supertype to check the condition against, C is the result if A does extend B, and D is the result if A doesn't extend B. Here, the open type is interrogating the state of the key input type based on whether or not it matches the password literal. If key match the password template literal type, the resulting type would be true, and if it does not match the password type, the result will be false. By converting the open type to some imaginary type function syntax, we can see this even more explicitly, that this is exactly like an if statement. But how does this help us identify our captor? There are lots of encoded messages being intercepted, but only some of them look useful. We can describe the messages with this template literal type. We can use a conditional type to filter out the invalid messages by checking if they match the template. If the input doesn't match the template, we reject the input by using never, the bottom type. With our first decode type, we can correctly identify the messages that we care about, but there's a lot of extra padding that isn't that useful. To extract the useful data, we need to use the main superpower of conditional types, inference. Within a conditional type, there's a special keyword, infer, which is essentially magic. Infer tells the type checker that what we want to extract is something from within the type. Here we're saying we want to infer the bit of the input that matches the string in the original template literal. And if the condition matches, we'll return that value. This means that we can extract successfully the character in the middle, the important part of the message. But there's actually still quite a bit of noise in the extracted data. We only want to extract letters, not other characters. And this is where template literal types can get a bit ridiculous. If you want to match an individual letter, you actually just have to write out the unions of all the letters. But doing that allows us to add another extends guard to the input type, which sets up the conditional clause to do the inference only of alphabet characters. So this third version of decode will successfully filter out all the invalid characters and only leave us with the good data. We're going to turn these little puzzles against their creator and use it to decode the messages. We just need to reorganize the bits of code again. Infer only works within the conditional clause, so it must be B. And we can see that to do can only exist in C because it's getting inferred from the B clause. But if we put this one back to the top, then hopefully it's working. Okay, cool. Looks like we're away hacking. It's working. I'm starting to see a message. What? Jeff Cross? His beard?
What? Impossible. I thought you were unappreciative and ungrateful. But now I can see
I have to admit, I was not expecting that. We should probably call Jeff and let him know that his beard is kidnapping people to force them to learn about TypeScript. So, we learned about the TypeScript type system, about top and bottom types like any, unknown, and never. We learned about type narrowing and using type guards. We covered template literal types and how they can be used to express all kinds of string types. We use map types to manipulate the properties of types. And we use conditional types and infer to interrogate types and make decisions. What's that light? I think it must be the way out. I guess Jeff's beard must have unlocked the door as it fled. Let's get out of here. Thanks, everyone. That was super fun. Slides are there if you want them. I'll tweet out a link later, and I'll catch you around the conference. Thank you.